What is really buried under Idaho's Sawtooth Mountains? Not just a pretty alpine skyline, and not just another stretch of rugged granite. Beneath those sharp peaks lies a long record of crustal stretching, molten rock that once rose from deep below, old fault strands that still break the ground in pieces, and ice that later carved the whole scene into something almost too dramatic to be natural. So, what built the rock in the first place? Why does the range sit where it does? And how can a mountain front look so solid on the surface while hiding a fault system that is more broken and complicated than it first appeared? The answer starts deep in Earth's past, long before the Sawtooths looked like mountains at all. The rocks at the core of the range are mostly granite and granodiorite, which are coarse-grained plutonic rocks formed when magma cools slowly underground. That single fact matters because it means the Sawtooths are not volcanic cones or young lava piles. They are exposed roots of a long frozen magmatic system. The Idaho batholith is the biggest piece of that story. It is a huge body of Cretaceous granite and granodiorite spread across central Idaho, and its origin is tied to subduction, the process where one tectonic plate sinks beneath another. In this case, the oceanic Farallon plate dove beneath North America during the late Cretaceous. As that slab went down, water and other volatile material were carried with it. Those fluids lowered the melting point of the overlying mantle and crust, allowing magma to form and rise. Some of that magma stalled far beneath the surface, where it pooled, cooled slowly, and crystallized into the granite and granodiorite that now make up much of the Sawtooth bedrock. The chemistry and texture of those rocks fit this story. They are coarse because they cooled slowly. They are intrusive because they formed at depth. Geologists call these deep intrusions plutons, and as dozens of individual plutons merged and cooled at different times and depths, they produced variations in texture and mineralogy across the batholith. In the northern Sawtooths, even younger pink Eocene granites, about 50 million years old, often called the Sawtooth Pluton or Sawtooth batholith, cut through the older Cretaceous rocks. These give some peaks their rosy hues. They are granitic because partial melting of continental crust produced silica-rich magma. That is not just a label. It is a record of a major tectonic engine at work. The important part is that the Idaho batholith did not form in one instant. It grew through many separate intrusions that coalesced over time into a broad composite mass. That is why batholiths are messy under the microscope, even if they look massive and uniform on a map. Different magma batches rose at different times, stopped at different depths, cooled at different rates, and created variations in grain size, mineral content, and texture. In the Sawtooth region, this matters because the mountains expose not a simple single pluton, but part of a broader crustal architecture built from many intrusive bodies. North of the main Cretaceous batholith, there are also younger Eocene batholithic rocks, adding another layer to the story. Those younger intrusions show that the region did not simply crystallize once and stop. It remained active enough, geologically speaking, for new magma to enter later. The mountain block therefore preserves more than one pulse of igneous activity, and each pulse marks a different chapter in the tectonic evolution of central Idaho. Once the magma cooled and hardened, the next long process began: uplift and exposure. Rocks that form several kilometers down or several miles down do not become mountain peaks by themselves. They must be brought up, or the overlying rock must be stripped away, or both. In the Sawtooths, crustal extension played a major role. As the western United States stretched during the late Cenozoic, normal faults developed. A normal fault forms when the crust is pulled apart and one block drops down relative to another. That is the key mechanism behind the Sawtooth Fault. It lies along the eastern base of the range and marks the boundary between the uplifted mountain block and the lower basin to the east. Over time, repeated movement on that fault helped create the steep front of the range. Each earthquake along the fault nudged the hanging wall downward and, in effect, lifted the range higher relative to its neighbour. This is how a fault scarp becomes a mountain front. It is a structural edge, not just a scenic one. For a long time, maps treated the Sawtooth Fault as if it were one clean line. That view was too simple. New LiDAR-based mapping changed the picture. LiDAR, which uses laser pulses from aircraft to build very detailed topographic models, can see subtle offsets that older mapping methods miss, especially where vegetation or glacial debris hides the bedrock. The new mapping showed that the Sawtooth Fault is not a single continuous crack. It is a discontinuous fault zone made of several strands. Some strands connect, some break, some step over, some are only obvious where they cut young deposits or form scarps in the landscape. The result is not one neat fault trace, but a fault corridor, a broken system of slip surfaces distributed across the eastern range front. That distinction is important because fault complexity changes how strain is stored and how earthquakes may rupture. A fault zone with multiple strands may not always break from one end to the other. It can rupture in sections. It can switch active strands through time. It can make paleoseismology harder because different trenches or lake records may capture different pieces of the same larger system. This complexity is one reason the Sawtooth Mountains have attracted so much scientific attention. The fault is active in quaternary time, which means it has moved during the geologically recent past. But its exact behaviour is not as straightforward as a single master fault line slipping in a regular way. Instead, the fault system appears to be segmented. That means stress may accumulate differently on different strands, and one earthquake may involve only part of the overall fault zone. The best evidence for this comes from geomorphic mapping, trenching, and lake sediment studies. Together, these tools allow geologists to reconstruct earthquakes that happened thousands of years ago, long before instruments existed. One of the key recent surprises is that the magnitude 7.5 number sometimes attached to the fault is not the cleanest summary of its likely size. Older reporting leaned toward an upper-end estimate, but newer paleoseismology gives a more careful range. A study published in 2024 reports evidence for partial to full rupture on the Sawtooth Fault and places likely rupture sizes around magnitude 6.8 to 7.4. That does not rule out larger events entirely, but it does make the fault look more bounded than the older, more dramatic claim suggested. In other words, the question is not whether the fault can produce a large earthquake. It can. The question is how large, and whether the whole mapped system can break at once or only in pieces. The evidence now leans toward an event around magnitude 7 being reasonable, while a firm magnitude 7.5 claim is less secure. That is not a minor distinction. In earthquake science, a difference of half a magnitude unit is a big shift in the amount of slip, rupture length, and released energy. The paleoseismic record supports this segmented view. Trenching across the northern part of the fault found evidence for at least one earthquake around 9,000 years ago. Lake sediments from Redfish Lake preserve evidence for earthquakes around 7,600 and 4,300 years ago. Sediments from Pettit Lake, about 15 kilometres or about 9 miles south, record another event around 5,100 years ago that seems to be separate from the Redfish Lake events. Those ages do not line up neatly into one single whole fault rupture story. Instead, they suggest that different parts of the fault zone ruptured at different times. That is exactly what one would expect from a complex strand system rather than a perfect single plane. Lake basins are useful here because they quietly archive shaking. A strong earthquake can trigger underwater slope failures, disturb sediments, and leave a layer or texture that can later be dated. In that sense, lakes become seismic memory devices. This is also where the one-off earthquakes in the area become important, not because of damage, but because they reveal structure. The 2020 Stanley earthquake did not rupture the Sawtooth Fault itself, in the simple sense many people first assumed. Careful analysis placed it about 16 kilometers, or about 10 miles, north-northeast of the mapped fault, on a nearby and more complex fault system. Aftershocks showed a north-trending plane dipping steeply west, parallel to the Sawtooth Fault, but in the opposite direction. That means the earthquake happened on a neighbouring structure, not directly on the main mapped Sawtooth trace. From a geological standpoint, that is fascinating. It shows that the crust in this region is not organised around one fault alone. It contains a broader fault network, capable of taking up strain in more than one way. The Stanley event therefore became a kind of stress test for the regional structure. It revealed that the area around the Sawtooths is tectonically busy in a hidden way, with faults that are not always obvious at the surface. To understand why this region can support that kind of complexity, it helps to think about the shape of the crust itself. The Sawtooths sit in the northern part of the Basin and Range Rocky Mountain Transition Zone, where extension, block uplift, and inherited crustal structures interact. When the crust stretches, older weaknesses can be reactivated. A pre-existing fracture, Pluton margin, or compositional boundary can become a preferred place for fault slip. The granitic basement beneath the Sawtooths is strong, but it is not uniform. Granite and granodiorite can fracture in different ways depending on joints, foliation, cooling history, and later alteration. Once extension begins, the crust does not always break along one newly born fault. It can exploit these older weaknesses. That helps explain why the Sawtooth Fault is a zone and not a blade. It also helps explain why nearby faults may exist without being obvious on older maps. The crust remembers the structures that came before. The fault's geometry also matters for mountain shape. Along a normal fault, repeated movement can tilt blocks, raise one side and drop the other. The uplifted side becomes a range front. Over time, the range front can become steep and straight where the fault is active, while river valleys and fans collect at the base. But the Sawtooth front is not just tectonic, it has also been reshaped by ice. During the Pleistocene, alpine glaciers occupied the higher valleys. These glaciers were powerful agents of erosion, and they did much more than just polish the bedrock. They widened valleys into U-shapes, deepened basins, cut cirques at valley heads, sharpened ridges into arates, and carved peaks into horns. In the Sawtooths, those glacial forms are everywhere. They are not decorative details. They are mechanical evidence of how ice moved through the landscape. A glacier is not a static block of frozen water. It is a flowing mass that scrapes, plucks, and grinds rock as it moves downhill. In a hard granitic mountain range that produces steep walls, jagged ridgelines, and over-deepened basins that later fill with lakes. That is why the Sawtooths look so sharp. The peaks are granite, but their current forms are glacially sculpted granite. The rock controlled the general strength of the terrain, while ice controlled the fine shape of the valleys and summits. Where a glacier removed enough rock, it left behind steep headwalls and basin floors. Where two glaciers eroded toward each other, they isolated a narrow ridge or horn. Where meltwater and debris accumulated at the margin, moraines formed and sometimes dammed lakes. Redfish Lake and similar basins are part of this legacy. The lakes are not random puddles in the mountains. They are direct products of glacial deposition and carving. That is why the Sawtooths hold such a clean example of alpine glaciation. The range gives you both the hard basement and the surface sculpting in one place. This combination of tectonics and glaciation makes the Sawtooths more than a scenic range. They are a record of two very different Earth systems working on the same landscape. The tectonic system created the rock and elevated the block. The glacial system sharpened and hollowed it, then faulting kept modifying the base. The mountains we see now are therefore not a final product. They are a snapshot in an ongoing process. The granite was born deep underground from subduction-driven melting. The crust later stretched and broke, lifting and tilting the block. Ice then carved the block into its present form. And beneath the surface, the fault system remains active, continuing to adjust the boundary between mountain and basin. A close look at the fault geometry shows why this system is still scientifically important. New LiDAR mapping identified additional scarps and strands that were not appreciated before. These include previously unmapped through-going scarps that show strong geomorphic evidence of surface faulting. When a scarp cuts young deposits or aligns with subtle topographic breaks that repeat along strike, it is often the signature of repeated earthquakes. In this case, the fact that multiple strands exist means that deformation may be spread across the fault zone. Instead of one massive rupture surface, the crust may use several linked breaks. That can lower the chance that every earthquake uses exactly the same path. It also means that the landscape itself can preserve a patchwork of ages and offsets. Some fans record one rupture, others record another. Some scarps may have formed in one event and been partly erased by erosion or later glaciation. That is why multiple methods are needed. Field mapping, LiDAR, trenching, and lake cores all fill different gaps in the record. The geology below the Sawtooths also reflects the broader history of Western North America. The batholith is tied to the Sevier and Laramide orogenic systems, which were major mountain-building episodes linked to subduction along the western margin. The magma that formed the batholith was not random. It was the chemical and mechanical result of a plate boundary regime. As the Farallon plate descended, fluids helped trigger partial melting. Magma rose because it was buoyant relative to the surrounding rock. It then stopped at mid-crustal depths, around 4 to 25 kilometers, or about 2.5 to 15.5 miles below the surface. There it cooled slowly enough to grow large crystals. That slow cooling is why granite looks speckled. The feldspar, quartz and mica crystals had time to grow. Later, uplift and erosion stripped away kilometers or miles of overburden, exposing those crystals at the surface. In one sense, the Sawtooths are an exhumed magma chamber roof. That is what makes their geology so compelling. What you see is deep earth material made visible by time. It is also worth noting that the Sawtooth Mountains are not just a passive display of old rocks. Their position and shape reflect the interaction between inherited plutonic crust and younger extensional tectonics. The batholith provided the strong crystalline basement. Normal faulting exploited weaknesses along the range front. Glaciation then overprinted everything with valleys, lakes and sharp ridges. The range is a stack of processes. Remove one layer and the whole story changes. Without the batholith, there would be no hard granite core. Without extension, there would be no sharply tilted fault block. Without glaciers, the range would likely look less jagged and less dramatic. Each process left a different fingerprint, and all three are still readable if you know where to look. The deeper lesson here is that a mountain range can seem stable while hiding a very active history of change. The Sawtooths appear fixed because time has made them look permanent. But granite can be uplifted, faulted, and sculpted. Fault strands can move in parts, then be hidden, then reappear in LiDAR data. Earthquakes can occur on nearby faults that were not obvious in older maps. Glaciers can carve sharp shapes into solid rock and leave them looking timeless. That is why the Sawtooths are such a strong case study. They show how one region can preserve the effects of subduction, plutonism, extension, seismic rupture, and glacial erosion all at once. So, what is beneath Idaho's Sawtooth Mountains? A lot more than a mountain range usually gives away. Beneath the skyline is a Cretaceous granitic batholith born from subduction-driven melting. Beneath the fault scarp is a segmented normal fault zone, not a single clean break. Beneath the glacial lakes is a landscape reshaped by ice. Beneath the older headlines about a possible magnitude 7.5 rupture is a more careful, more technical picture. Likely earthquakes around magnitude 7, with the larger fault system behaving in a segmented and partly hidden way. That is the real shock. Not that the mountains have a secret, but that the secret is a layered geological history written in rock, fault, and ice. The Sawtooths are not simply standing there. They are still telling the story of how continents deform, how magma cools, how faults split the crust, and how glaciers can turn solid granite into one of the most striking mountain landscapes in the interior West.